Good evening. We'll start in a minute. Please wait for a minute for others to join. Thank you. Okay. So, good evening, everyone. Let me start the session. Um, Today is the week 5 of our problem solving session. Um, those who are joined new today, let me introduce myself. This is Saravanan, PMRF scholar of NIT Tiruchirappalli in Civil Department. And I am taking this NPTEL course as a part of TA-ship, PMRF TA-ship. This is my fourth session in NPTEL, and I have taken air pollution control, integrated solid waste management, and plastic waste management. And this is the fourth course I am taking, wastewater treatment and recycling, as a problem solving session. So my session will be on every Monday 6 to 8 p.m. So the course was taken originally by the instructor Dr. Manoj Kumar Tiwari sir from IIT Kanpur, and 2 hour session will be like 1 hour. I am going to take the same lecture material what sir has taught in the classes, and another 1 hour we are going to solve the old assignment problems. Okay, so first week we have discussed about the basics of wastewater, the sources of wastewater, and how to quantify the wastewater. Okay, in the second week we have discussed how the population is changing, how to predict the future population to design the wastewater treatment plant. In the third week we have discussed about the type of treatment systems, and in the fourth week we have discussed about the reactors, and today we are going to discuss about the primary treatment systems. Okay, so wastewater treatment system, actually if you have visited most of the sewage treatment plant, that is STPs in your municipality or corporation, this will follow the similar pattern of wastewater treatment systems. So we are going to discuss about the primary treatment system today, that comprises mostly of grid chamber, um, screens, and um, primary settling tank. These three are our today's content agenda. Okay, so I hope last week you have gone through the problems, the basic problems of reactors and all, and this week also we have some minor problems that is easy to understand, similar to kind of aptitude problems. Okay, let me go through the lecture material. If you have any doubt with the last week assignments, you can ask now, or I will go through the session. Yeah. Okay, let me start the session. So, hope my screen is visible to everyone. Let me start. Okay. So, yeah, thank you so much. So, this week we are going to see about the basics of municipal wastewater treatment. See here, what is the purpose of our wastewater treatment? As we are discussing from the first week onwards, this inlet containing lots of wastewater parameters, as we have discussed, like pH, color, turbidity, alkalinity, metals, organics like BOD, COD, nutrients, everything will come in this wastewater as a inlet, in the inlet. So after treatment we have to discharge as per the effluent discharge standards. So it should be a clean water, because we are going to dispose in a river or lake or pond or any water bodies, or in the inland surface, or any marine water bodies, so that it should be clear. Otherwise it will create lots of problems. That also we have discussed, what are the problems if we not treat the wastewater. So that's the purpose, right? So how this is converting from this to this, that comes the treatment system. So objective for wastewater treatment system is, whatever the wastewater collected from various communities, that need to be treated, so that we are ensuring no danger to the human health and damage to the environment. That much treatment need to be attained. So extract and remove various pollutant is the main objective. Then how much we need to treat? The degree of treatment is majorly based on how much the what are the characteristics of that raw wastewater, and also based on the desired quality of the treated water. For every disposal option, we have a desired quantity, right? So that is governed by the state regulator water wastewater discharge standards, and also based on water quality standards that is prescribed in the local bodies or ministries given guidelines. So if you see the guidelines, first one is the EPR rule, Environmental Protection Rule 1986, that given various parameters you can see here in the first column, discusses about the discharge standards of each option. If you see the first option, inland surface water. Second option is public sewer. If you are discharging in the irrigation land, and fourth option is the marine coastal areas. So based on the uh, place where you are going to discharge, the environmental protection rules have prescribed the standards. That is Schedule 6. If you see, Part A will be the effluent discharge standards. They have prescribed more than 33 parameters here. Okay. So another standard based on MOEFCC, that is Ministry of Environment, Forest and Climate Change, they have a notification amended whatever the already available rule in 1986, that was amended in 2017. So that also you can see in the Gazette of India. So environmental production rules, that is amended rule in 2017. What are the parameters they have changed? Initially the BOD was 30 in the discharge standard. If you see BOD where it is here, 30 is the minimum BOD. Then they have changed it to 20. So we have to treat 10 more milligram per liter of BOD in metro cities. Other regions will follow the same 30 milligram per liter. And TSS, if you see, they have reduced it to less than 50. And then fecal coliform, they reduced it to less than 1000. Like that, they have amended different changes in the already existing rules. Then another standard is USEPA guidelines. So they have different prescribed different treatment technologies based on types of reuse. If you are going to reuse for the urban sources, you have to do a secondary treatment, filtration and disinfection. If you are going to use for agricultural reuse, what is the required water quality parameters you need to see. And then if it is for the food crops commercially processed, then what we need. Like that, based on different reuse options, they have prescribed the different quality standards and the treatment systems. And another guideline given by WHO, World Health Organization, for the microbial quality. So it mentions the essential, the E. coli, that is the coliform count. If it is going to be discharged in the irrigation land for crops and all, what should be the fecal coliform? What should be the helminth egg? Helminth egg is small eggs that is present in the wastewater. That also need to be counted per liter, and that need to be less than 1. That is also human health risk factor. And then FAO have a separate guidelines. FAO is Food and Agricultural Organization of India. So they have a separate guidelines for the trace metals in the irrigation water. So this much of trace metal we need to uh, determine, and we have to compare with the standards. If it matches or less than the standard only, we have to discharge the irrigation field. Otherwise, it cannot be used as a irrigation water. Similarly, FAO guidelines, they have given interpretation of water quality for irrigation. This is for trace metals. This is for other parameters like salinity, EC, and TDS. Okay. Then if you see so these are all guidelines. So you know how much we need at the end. You know how much is coming in by based on the characteristics of water. So we can find how much treatment is required, so that we can design the treatment plan, right? This is the basic. We know the characteristics of wastewater. We know how much it should be at the end based on the described guidelines. Then we can find how much treatment we need to give. Now, if you see what is the wastewater treatment process, it is a several step process, not by one simple tank or a reactor you can treat all the things. So we need to have a combined system or different treatment steps, so that it will reduce. Initially BOD will be 100. First step it will reduce to 90. Second step it will reduce to 80. And in the biological system it will reduce to 30. Like that, we are treating in a subsequent manner. Based on that, we are dividing the treatment system into unit operation and unit process. So those are two major categories. What is unit operation? That will comply only physical forces. That type of treatments are called unit operations. For example, if you do screening, if you do grid chamber, if you do sedimentation, no chemicals are involved or no biological system is involved. Only on physical process by sedimentation, by gravity, or by filtration, like that. This type of these things are all called unit operations. If you think about unit process, that will have both chemical as well as biological reactions like biodegradation, chemical degradation steps, flocculation, that are all unit processes. Okay, so if you see the typical STPs like sewage treatment plant, it have a combination of several unit operation and unit process for the complete treatment of wastewater. So this is the typical municipal wastewater treatment process. See, first is preliminary. It will have a screening, cumulators, and grid chambers. Screening is the one which will filter the water. Filtration in the sense filtering the larger compounds. Then cumulations will break down the larger particles, and then grid removals will remove the settleable solids like big sand particles, grid particles. It will remove. Then it will move on to the further processes. Primary treatment, it will have sedimentation, simple primary sedimentation tank. Then secondary treatment will have biological systems like ASP, trickling filters, kind of things. Then advanced treatment process will remove the nutrients. Here we will remove the organics. Here we will remove the solids. And advanced process will remove the nutrients like nitrogen, phosphorus, potassium, and heavy metals. That all will be removed. Disinfection will come in any process. If you want to treat only with the primary treatment, you can do sedimentation and you can do disinfection and you can discharge. If you want to do secondary, after secondary you can disinfect and you can remove the effluent. After tertiary also you can do disinfection. So disinfection is mandatory for any purpose. So preliminary and primary treatment are grouped together and called as primary treatment plant. Oh, sorry, primary treatment system. All this will come under primary. That was we are going to discuss today. So preliminary treatment contains screens that will remove the large floating particles like screens will come, the grid chamber will come, and the breakdown of particles by accumulations. And then primary treatment will follow uh, physical settling of insoluble solids. And then secondary treatment will follow biological treatment that will remove the organics. Then tertiary treatment will remove nutrients, ITDS, microbial. Whatever we had seen in the last diagram, that's what discussed here. Okay. So if you see the examples of wastewater treatment plant, these are the examples like Nagpur wastewater treatment plant, South Bend. If you see, these are all initial screen. After that, a primary settling tank is there. After sedimentation, it will go to the aerators, ASP. After ASP, again secondary settling tank, and then the effluent will be taken and it will be moved to the disinfection chamber. And there are some of the external aerators or kind of things will also be there. So this is a proper typical wastewater treatment plant. You can see here some of the tanks required for biogas production from the sludge. Some sludge will be taken and used for sludge thickening tanks. So these are all whole treatment process we are going to see. So first preliminary treatment is screening. So screening is simply you will have a bar. Okay. So water will flow through this. Larger particle will be retained. Only the water with smaller particles will move on. If we not remove this type of larger particles, it will affect the mechanical equipments in the upcoming steps. So we have to first remove the larger particles like suspended particles, floating coarse materials, pieces of cloths, wood, leaves, plastics, rags, papers, that all will be removed here. Okay. So this is the first unit operation process because it's not involve any chemical or biological. It's only by physical separation. It's a unit operation. So must be removed at the beginning of the treatment so that it will not damage the subsequent process equipments. So what is the types of screen we can use? Parallel bars we can use like this. Gratings we can use. Wire mesh like this type of mesh we can use. Perforated plates. A plate contains different types of holes we can use as a screen. So anything we can use as a screen. The openings are usually rectangular or circular. Based on the size, we can divide the screens into coarse, medium, and fine screen. So coarse screen will have a size of 6 to 150 mm. Fine screen will be of less than 6 mm and the micro screens will be of less than 0.5 micrometers. So these are the screen sizes we can see. So core screen will can be cleaned by hand cleaning and mechanical cleaning. Again, it will be based on chain driven or reciprocating rake. And fine screen will be having static wedge wire drum step, like this kinds of fine screen we can find. So core screen, if you see, as I mentioned, 6 to 150 is the opening size. It will be of bar or bar rack. So because you should remove only the coarse particle, so it will be having bigger size of opening. So bars we can use as a opening. And then protective device will be there. And then a bar composed of vertical and inclined bars. Why we need an inclined instead of straight bars? Because inclined bar will increase the area of flow. If you are having this is the area, you have a depth, you have a width, and you have a length of the bar. So L into W will be there. But if you put the same in slanting, and this thickness will be W. So this height will be L. So same, if you see the slanting length will be L square plus W square. It's increasing. So increased area will be there for slant screens. That's why it's placed in a 45 to 60-degree angle always. So that's the top view. If you see the top view, water will come through the pipe. That's the approaching velocity. It will move through the screen. That is the flow through the screen, and then it will reach the next channel. So like that, if you see from the top, it will be like this. So if you see from the side view, there is a slanting screen. The water is flowing through that. Particle will be trapped here, and it will be taken out with some mechanical or manually we can take with the racks. Okay. So cleaning, how to do coarse screen cleaning? We can do hand cleaning or mechanical devices. So mechanical cleaner utilizes chain and cables that will always move. So whatever the particle trapped here, that will move and put it in a separate tank here. Okay, it will move with the belt, and it will be taken care in the separate tank. And hand cleaning, if you do, always it will be with at 45-degree, right? So you can increase the effective cleaning surface, because you can rack with the hand with a kind of shovel. You can take and you can remove the trapped solids. Yeah. So medium screen size will be of 12 opening and 10 thick, and it will be used before all pumps and treatment units. So if you have a kind of a pumping system, and that need to be uh, so before any pumping system, you need to have a medium size screen that have a 12 opening. Okay, that may be of rectangular in cross section, and 10 cross 50 will be the size. So fine screen, if you see, it will be a plate with the perforations. So that can be used as a fine screen. Small openings will be there, like 6 openings and all. So fine screen used for pre-treatment of industrial wastewater. It will not be used for domestic wastewaters, because we have a larger particles that will easily clog the fine screen. So industrial process which do not have larger particles, we can use the fine screens. Okay, so not normally suitable for sewage because it will clog. How to use the fine screen? It will be of drum type or disc type. It will go through this and it will come out like that. Drum screens also there. So drum will be there having perforations. So if water is passed through the center of the drum, clean water will come out through the periphery. Like the drum screen we can use. Okay. Then micro screens, that is mostly for industrial purposes. For secondary effluent treatment, stabilization pond, after treatment you can use the micro screens, and not very popular for municipal wastewater treatment due to its disadvantages, including improper removal of solids. Then accumulating devices, that is a grinder actually. So it will have a hard material with teeth. So that will break down the coarser particles, and it will be converted into smaller particles, and it will move on with the water, so that it can settle in the grid chamber in the next channel. So initially we are having a screen, then after passing through the screen, we have a grinder. It's optional part. So through this grinder, the coarser particle will be converted into smaller particle, and it will go again. It will go to the grid chamber. There it will settle, and clear water will come out. So this is the primary step. Okay. So it will cut down the retained solids and enabling them to pass through the sewage. So recommended for smaller sized STPs, because if you are having handling 5 mld or 10 mld plant, you can't break all the particles. So smaller STPs with 1 mld size, we can use this type of grinders. So where can we use this screen? Screen will always be placed at the starting of the treatment system. So it will be because always it will be readily accessible. We have to remove the solids often. Frequent inspection and maintenance is required. And screening chamber should have a house because we are having a screen, so it should have a house. Okay, so that we can it will not have a other contamination. Mechanical clean the screen need suitable housing, ensure proper operations. So we have to have a hydraulic operation system for this type of screens. Any screen, if it functions, it will have a clogging and the pore size is also less. So there will be a head loss. Initially, there is a head here. So the head loss will be there always when the water passes through the screens. So that hydraulics we are going to see. Okay, in the other continuous cleaning arrangement required. Otherwise, periodic cleaning arrangement may cause surge in the flow of the water. So the surge is called the increase in the height of the inlet water. That's the head loss. Okay. So base of the screen is always placed a few centimeter below the invert of the base channel. That you have to take care. That uh, increase in some depth at the inlet is required so that it will handle the head loss. And velocity, if you think about the velocity of through the screen, it will be of 0.8 to 1.2 meter per second. That is higher velocity only, should not be less than 0.3 meter per second. And velocity of 0.8 meter per second is the average thing. So through the screen it should pass through 0.8 meter per second. Okay, a straight channel considering the screen assures good velocity distribution. So how the head loss will be calculated? Head loss will be calculated with an empirical formula 0.0729 v square minus small v square. So what is small v? What is capital V? Capital V will be the velocity through the screen, and small v will be the velocity before the screen. That is the approach velocity. So you have a screen. So the water is coming. That is the approach velocity small v, and it's having a small pore size. So velocity will increase to capital V through the screen. So capital V square minus small v square. Small v is the approach velocity. Capital V will be the velocity through the screen. Okay. So that both you have to know, and you have to substitute in the formula. You will get the head loss. Okay. Head loss will usually be 0.15 meter. If it exceeds 3 meter, the screen got clogged. So you need to clean. So based on the head loss, you can understand whether the screen is clean or not. Okay. Then if you see the head loss through the screen with another formula, that is Kirchmeister's equation, you have beta W by B 4 power 3 HV sin theta. So this W and B will be based on the width and the breadth of the screens or bars, okay, and the clear spacing between the bars. So these are two are bars, and this is the spacing between the bar. Like that, we have arrangement of bars. Okay. Then beta is the shape factor. If it is a sharp edge or a rectangular or circular bar, we can use this value as a factor. And actually will the velocity head of the flow. Yeah. So theta is the angle of inclination of the screen, maybe 45 degree or 60 degree. If it is a fine screen, you can use this formula to find the head loss, 1 by 2g q by ca square. C will be the coefficient of discharge, A will be the effective submerged area. That's the opening area. Okay. Only the submerged area. What is up to here, then how much area is submerged opening area, that you can find. Usually we have to use the bar screen with this formula. That's the basic formula we are using, 0.0729 capital V square minus small v square. Others you can just know. Disposal of screenings. So what we can do with the trapped material that is collected with the mechanical rack, and then it's stored in a separate tank, right? What we can do with this collected screen? Always it will be of range 0.035 to 0.03 meter cube per 1000 meter cube of water. If you take 1000 meter cube of water, you will get 0.03 meter cube of solids. So that need to be disposed in a sanitary landfill. If it is not having any organics, if it is having organics, it need to be dried and then it need to be disposed in the sanitary landfills. If you have a grinder, you can grind it, and if you do incinerate, you can also do incineration, but if the water content is less. Then what can we do? Next process is grit chamber. So first the water passes through the screen, larger particles are removed, then it passes through the grinder, where the smaller particles are again grinded into even more smaller particles, kind of grits. Then it passes through the grit chamber. Grit chamber is a rectangular chamber where the grits, that is the again the larger particles like silt kind of sand kind of particles will be removed here. So that passes through the grit chamber and it will be removed. How can we so this all our unit operations are preliminary treatment. So grid chamber is the second unit operation and it removes the grid. Heaviest particle will be removed like sand, gravel, cinders, coffee grounds. So that's having a specific gravity of 2.4 to 2.6 easily will settle, right? If it is having unit specific gravity nearly 1, it will move with the water. If it is less than 1, it will always be in suspension. If it is greater than 1 or greater than 2, it will be easily settleable and it can be removed in the grid chambers. So it will protect the further equipment. Same principle is followed. So non-putrescible grids are there. It can be having higher hydraulic subsidence value. Yeah. So these are the types of grid chambers you can see: V-shaped, square-shaped, vortex type. Based on CPHEO manual, METAF and AD book, you can follow, or EPA fact sheet you can follow for different kinds of types of grid chambers. Yeah. Here, if you see the design of grid chamber, there is a formula. How the grid chamber works, the water is coming in with the solids. So, before it leaves, the solid should settle, right? That's the principle. How the solid will settle based on the gravity. So, that's the principle of grid chamber. The particle should settle on its own by gravity before the water leaves the tank. So, this is much length it should pass and this much height it should settle. So based on this factor we can design the tank. So velocities are essential for design of grid chamber. How to find the velocity? That is the settling velocity. So it's similar to the sedimentation tank. Simply we are sedimenting the particles, right? So based on the size of the particle, we are going to design. So if the particle is this much and the diameter of the particle, always assume the particle as a spherical particle and you can get the diameter of the particle. As per the CPHEO manual, minimum size of grid will be 0.2 mm and specific gravity of the grid is 2.65 as I mentioned earlier. So if you have a settling velocity formulas, this is based on Newton's law, small vs, that is the settling velocity equal to root of 4 by 3 g cd. Cd is the drag coefficient, g is the acceleration due to gravity, and the unit weight of solids minus unit weight of water by unit weight of water, this is 1000 always, into d diameter of the particle. If the flow is transitional, if the flow is non-transitional or laminar, you all know about the hydraulics, right? When the water is passing, you can when the flow is there, you can find the Reynolds number of the flow. If it is a laminar flow, it is slow water, I mean slow movement, or no more turbulence is there. If it is a turbulent water, it is having higher velocity and turbulence. So RE will be always greater than 1 for turbulence water. RE is less than 1 for laminar flow. Turbulence flow, laminar flow, this is the difference. And in between this, it will have a transition flow. Okay. So if you slowly open the tap of the uh, water tap, you will find the laminar flow. If you suddenly open the tap, you will find that turbulence flow. That is the difference. So when the water is flowing in a laminar flow, Stokes law is valid. You can easily find the settling velocity with this formula: GD square by 18 mu G minus 1. That is the specific gravity of the solids minus 1. Okay. So this is the basic formula you have to remember. Settling velocity is based on the Stokes law. Stokes law is GD square by 18 mu G minus 1. So based on the Reynolds number, you can find that the Reynolds number is 1 to 1000. It will be a transition flow. You can use this formula. The Reynolds number is less than 1. It's just laminar flow. You can use this formula. It will always follow laminar flow only. It will be always. And if it is in turbulence flow, you can use this formula or Hazel's modified formula for the temperature of water is taken into account and it has calculated. Okay. So how to design now the grid chamber? We have to know the another parameter called surface overflow rate. Surface overflow rate. How much meter cube of water meter cube per day of water is going through 1 meter square of surface area. That is called surface overflow rate. If it is the top view of the tank, water is coming in, water is going out. So this much area, surface area is taken. Top view. I am saying about the top view. How much flow is there? That's called surface overflow rate. That is again a velocity, right? Meter cube per day per meter square. If you cancel the meter square, you will get meter per second, right? So surface overflow rate is on rate of flow. That's the velocity again. So whenever the settling velocity, whatever we had discussed earlier, if it matches with the surface overflow rate, that is the SORV, then the particle is settled. If it is less, then the particle efficiency is reduced. If it is more, 100% particles are settled. You understood the concept. Settling velocity, if the settling velocity is 1 and the flow velocity is zero 0.1, then all the particle will easily settle because it's more faster settling. If the settling velocity is 1 and the flow velocity is 2, so water is moving faster. It will not settle. Only 50% of will be settled. So 1 by 2 will be 0.5. That's the efficiency. Efficiency of removal of grid will be settling velocity by surface overflow rate V0. You got it? This is the basics of grid chamber. So always you have to find the SOR, and it will be how to find SOR. Q by A. Q is meter cube per day. Area is meter square. So Q, you know, A is surface area because it stop you length into breadth, not the height. Height will come in settling velocity. Okay. Another major formula is detention time. Detention time will not exceed 60 seconds. Every tank will have a detention time. How much time it will take when the first particle of the water enters into the tank and it leaves the tank. How much time it takes to cross from this point to this point is called detention time. Detention time is the time the water particle is inside the tank. So it will be less, very less for the grid chamber, only 60 seconds. If you think about plain sedimentation and all, it will be 30 minutes, 20 minutes like that. Okay. Particle enters and it will take 20 minutes to travel. That much we have to reduce the velocity, then only it will be reduced. But grid chamber, it will be always 60 seconds, not more than 60 seconds. Yeah. So if we take the Shields formula for scoring, what is scoring process? Once the particle is settled, it should not again come back into the water suspension, right? That is called the scoring process. Because if you increase the velocity of the flow, whatever the particle settled will again come out. So that need to be taken care. So I have to find the scoring velocity using this formula, and I have to compare the flow velocity. If the flow velocity is more than the scoring velocity, the settled particle always come in again to the water. So always you have to maintain a flow. It should be less than the scoring velocity. Okay. And you have to have a free board. Free board will be there in any tank, so that if extra water comes in, it will take care. So 0.6 meter will be of nominal head loss that need to be taken care with the free board of 150 to 300 mm. Then how to clean the grid chamber? All the particles are settled, so it will have a settlement here. So this particle need to be taken manually or mechanically, and it need if it is less than 1 mld plant, you can do manual cleaning. If it is more bigger plant, you can use the mechanical cleaning of continuous or intermittent. Continuous is always it have a rack that will move in a chain. So that rack will drag all the grids to the end, and it will have a hopper here. So that will collect the grids. Okay, that's one of the type. And then intermittent will be sometimes it will store and it will take out based on the capacity. See, these are the grids at the outlet. So clean grid is odorless because grids are not organic. So it will easily settle. The particle is having 2.65 of specific gravity, it will be always non-organics. And disposing by dumping or burying. If not wasted, grid particles may contain organic matter or other compounds. So available for, based on the land availability, you can think about sanitary landfills or something for the disposal of this type of grids. Then comes the equalization tank. That is again optional. Why we need a equalization tank? Always the flow will not be common. Morning, more water. If you think, sorry, if you see the graph between the volume and time, morning 8 o'clock more water we are using, and again 12 o'clock we are using less water. Again after evening we are using more water. So the STP cannot be operated same at any time, right? So more water should be handled at the morning, less water should be handled at the noon. Like that, there is a fluctuation in the water quality and quantity. Quality also will vary. Morning more dilution, quality will be poor here. So we need to have a tank that will hold all the water stored in a day, and then we are pumping in a actual rate. So we can, this rate will be always fixed. So we can supply a same quantity of water to the STP. So we need a tank that will equalize the flow rate. That's why it's called equalization tank. It will equalize all the characteristics, right? If you are storing only 5 liters and then next batch another 5 liters, that property will vary. But I am storing both all the 10 liters and then taking from this, the quantity will be similar in all the 10 liters. That's the purpose of equalization tank. What's the objective? To balance the fluctuation, flow fluctuation, assist in self-neutralization. If the pH varies, all the water will come in the industry process and it will mix and you will get a neutralized water. Then even out the effect of periodic sludge discharge from the batch process. These are all objectives of the equalization tank. Yeah. So what is the benefits? Shock loading can be eliminated. If morning and all, you will have a huge load of water. So that is a shock load that can be eliminated. In the effluent from the biological treatment, yeah, then the effluent from the biological treatment have a better quality because you are having a same kind of water coming into the STP. Before STP, you have a utilization tank. So that will store all the water and then we are pumping. So all the water that is coming into the STP will have the same quality and the quantity. So that have a improved treatment process. Okay. And risk of plant failure will be reduced because we are giving less shock to the treatment system. So we can design based on three types like flow through type, intermediate flow type, variable inflow, constant discharge type. So all see here, all water are coming in and then first tank is already filled, it is taken. Then second tank is filling, after it fills, it will be taken. Like that, we can have a fill and draw type. Okay, where we can place the equalization chamber. Volume requirement is based on the inflow cumulative volume diagram. See, morning it's cumulative diagram. I'm saying about the morning it's high, afternoon low, morning after evening a high. So if you add all the values and draw a cumulative value, it will increase and straight line and again it will increase. The difference between the maximum and you have to find the slope for this line and this point, and the difference between these two slope will give you the cumulative volume required to be stored. So that is the volume of the equalization tank. So volume requirement is based on the inflow cumulative volume diagram against the time per day. Okay. So where I can place the equalization tank after the grid chamber, or I mean this is inline. If you are using the grid equalization tank out of the line, then it will be always flow will be there. Whenever excess flow comes, it will be taken care by the equalization tank. So this is offline, right? Then the fourth step will be, first will be screening, then second grid chamber, then third part will be primary clarifier or sedimentation tank. Sedimentation tank will remove again solids which will have uh, very less size like silt, clay particles, kind of settleable organics particles will be removed in primary clarifier or primary sedimentation tank. So that's the suspended organics. We are having large time to pass through the tank so that all the solids will settle, right? It's essential for phase separation process because phase in the sense solids and liquid phase we are separating. Solid will settle down, liquid will pass through. That's the phase separation. So sedimentation tank acts as a phase separator. You got it? Yeah. So what are the things is settling in the sedimentation tank? The main principle is by gravity only. So to settle out the suspended particle due to gravity, suspended materials like clay, silt, coagulation, flocculation process. After coagulation, flocculation, we have a bigger particle. Coagulation, flocculation, we are going to discuss in the next week. I mean, in the water treatment, we will do. So all the smaller particle will mingle together to form a bigger particle. That's a flog. That flocks will easily settle. So that kind of things also will happen in the sedimentation tank. And then biomass, after biological treatment, the bigger biomass will settle. Okay, so we need to decrease the velocity, so slow down, so that the water entering will slow down, and before it leaves, due to gravity, the particle will settle similar to the grid chamber. But grid chamber will have a high velocity, only removes the bigger particle. The sedimentation tank will remove the finer particles with reduced velocity. So we need to know what are the types of settling. So we have a four type of settling. First is discrete settling, second is flocculent, third is hindered settling, fourth is compression settling. So where this type of settling will happen? First, what are this types of settlings? First, discrete settling. That means each particle will settle on its own. This particle will have a separate velocity of settling. This particle will settle separately. This so one will not interfere with the other settling. That's called a discrete settling or free settling without any interaction under low solids condition. You can find the solids like somewhere not as a high concentration. With the low concentration, it will easily settle on its own. Second type is flocculant settling. All the particle will come together to form a bigger particle, then it will settle. That kind of settling is called a flocculant settling. Initially, it will be independent, and then with the depth, initially it will be independent, but it will merge with the other particle at deeper depth, and it will settle. Okay. Then third type is hindered settling. Uh, Settling of one particle hinders the settling of other particle. Because if I am moving in a race, the one who is running near me will also drag. So that kind of dragging is called hindered settling. You understood? So one particle is settling, that will drag the other particle to settle. So it will also be of um, fixed position with respect to each other. But this is settling separately, but this is also settling separately. But this velocity affects this velocity. So both are settling at a same rate. But it's a discrete particles only. Okay, that's called hindered settling. Then compression settling. Compression settling is having so high concentration. Here, particles are compressed based on gravity. All are already settled. Again, it will have a settlement due to compression. That is the weight of the above particle will settle the below particles. So this settling velocity is drastically reduced. No more velocity. It will settle based on weight. So if you think about the velocity, Vs2 will have higher velocity because of larger particle than Vs1, then Vs3, Vs4. So this is the order of settling velocity. So how the settling is happening? As I mentioned, everything is based on gravity. We are not giving any chemical reaction treatment. Only due to physical process like gravity, it's settling. So consider any particle as spherical particle. Whatever the dimension the particle is, we can consider as a spherical particle. So what the force is acting? Downward force is gravity force. Downward it will pull. Because it's in water, there is a buoyancy force. Whatever the things present in the water that have a buoyancy, right? So that is the buoyancy force Fb. And then once the particle is settling downwards, there is a drag from the surface that is called a drag force. Not only in the two sides, on the whole circumference it will act. If you think about a semicircle, you can find here, everywhere, the drag force will act. Okay, upwards. Because gravity is pulling downward, the drag is pulling upward. So that's the drag force. So whenever a particle settles in water, gravity will act downwards, buoyancy will act upward, and then drag force will also act upward. So please calculate the forces. F equal to ma. That is the formula of force. So gravity will be m into g, right? This is also acceleration due to gravity, right? So m into g will be gravity force. uh, Mass of the particle will be, how to find mass? Kg will be kg per meter cube into meter cube. You will get the mass, right? So meter cube is the volume. Kg per meter cube will be density. So density of the particle into volume of the particle. Pi d cube by 6 will be the volume of the spherical particle into g. Similarly, Buoyant's force, if you find, only the mass will change, because whatever the body in water, that will have a weight of the water that is displaced by the body. So same volume of water will be displaced. So same volume of particle will be equivalent to the water, but the so density of the Buoyant's force will be of water's density. You got it? A simple calculation you all know, I think. So physics only. If you have a particle that will drag by gravity, that will be acted upward by the buoyancy force. Similarly, drag force will also apply. How to find drag force? That is the equation called rho v square by 2 into cd into a, drag coefficient and area. So fb plus fd equal to fg. So if you upward force is equivalent to downward force. So gravity force minus buoyancy force will give you the drag force, right? If you do all the calculations, you will get this formula based on Stokes law. GD square by 18 mu g minus 1, or GD square 18 mu. If it is a dynamic viscosity, rho p by rho w. If it is a kinematic viscosity, g minus 1. Okay, please know this formula. Only Stokes law will be always useful. And transition flow you can find, if it is a laminar flow you can use this formula. If it's a transition flow you can use this formula. How to find laminar or transition? Laminar flow will have a Re less than 1. Transition flow will have a formula Re greater than 1. How to find Re? Rho Vd by mu is the formula. How to find CD? R24 by Re. Okay, first first assume if it's a laminar flow and calculate the settling velocity, and then with the settling velocity calculate the Reynolds number and confirm that is less than 1. Okay, yes. Now ideal settling tank, how to find its ideal settling tank? If it is the ideal settling tank, all the particle entering should settle. So assume the particle at the top. One second. Sorry, I'm sorry. So think about the particle at the top. So that need to be traveled a long distance to settle, right? In compared to this particle, it will easily settle. This particle will take longer time to settle or longer distance to be traveled. So I am taking the particle that is just entered in the tank at the top. Need to be settled at this much distance. That is the height of the tank. Need to be uh, traveled before the water travel to this much distance. You got the concept. The water is entering into the tank, so the particle at the top need to be settled to a distance of h before the water leaves the tank with a distance of l. If it traveled to the distance of l and the particle have covered only this much, that will go out along with the outlet water. If the particle comes here before at this point itself, it is settled, considered settled. So we have a four zone: inlet zone, outlet zone, settling zone. That is, sorry, this is the settling zone, this is the sludge zone. You got it? So here the settling will happen, here the sludge will be contained. Understood? We have assumption all the flow should be laminar, impurity particles are evenly distributed, kind of thing we are assuming. And then like all the particles are entering like this, evenly distributed. That's what our assumption, but it will not happen usually, but this is the ideal sedimentation tank we are considering. And the entrance and the exit does not affect the sedimentation process, and suspended particle is not coming into again, resuspension is not happening. That's the assumption. Once settled, it is settled. So inlet zone will be the water entering zone, and the smooth transition should be there, otherwise the particle will be disturbed. We can use the baffle to evenly distribute the water. Water is coming through a small pipe, and we can have a baffle so that it will enter into the tank smoothly. Okay, and then settling zone. This is the zone where the particles are trying to settle with the velocity of settling velocity. It's a calm area. And then sludge zone at the bottom of the tank, all the sludges are stored. Then outlet zone, smooth transition. We are giving this type of outlet zone. We can also use weir. If it is a circular settling tank, water is coming through the center, and it will be settled, and it will go out from the periphery or the circumference with through the kind of weir. V-shaped notches will be there. So that's the outlet zone in the circular tank. Okay. Then sedimentation basin will be of classifications based on the intermediate and continuous type. If the tank is a batch reactor, water is coming in, it will settle. After some time, it's taking out. That's the intermittent type, or quiescent type of tank. Water is stored, take complete rest so that the particles are settling, and then treated water is taking out. But continuous flow, water is coming in and going out. Before it leaves, it should settle. That is continuous type tank. Similar to batch reactor and continuous reactor, this is the type. Another type based on the shape: rectangular tank, circular tank. Okay. Am I audible now? Is my voice interrupting still?
Yes, sir. Yes, sir, but many times I have observed that your voice is interrupted, sir.
I'm so sorry. Now is it fine? Others are facing the same issue, or
Yes, sir, it is fine.
okay?
Others, please say it is for me. I am only facing the problem, or others are also.
That's what I am asking. Is it my internet issue or SARS internet issue?
No, I'm able to hear properly.
Okay. Then sir, please check your internet connection. Maybe I'll also try to increase my voice. Yeah. Yeah. Okay, thank you so much. So based on the type,
Okay, thank you,
uh,
sir.
intermittent or continuous you can use, or rectangular or circular you can design. Okay, yeah. See here, rectangular sedimentation tank, inlet is here, uh, settling zone is here, outlet zone is kind of a weir, and then sludge zone is there. How to remove the sludge? We have a weir at the bottom, we have a rack, so the rack will move and it will scrap all the grits or the sediments into the hopper. It will be retaken care. Okay, if it is a circular sedimentation tank, think like this. The water is coming through the center and it will move. Okay, enter into the settling zone. This is the inlet zone. This is the settling zone, and outlet will be of weir type. See this whole thing, circular thing. Water is entering from the center, and it will be flowing. And before it move from here to here, particles are settled at the bottom. So it's a hopper type at the bottom. So all the solids will be collected here, and then it will end outlet zone will be here. You got the concept of sedimentation tank, right? Now we have to design the sedimentation tank. How to design? As I mentioned earlier, settling velocity need to be equal to the flow velocity. Then only all the particle will settle. If the flow velocity is more, particle efficiency will be reduced. If the flow velocity is very less, all the particle will settle. But we should not maintain that much slow flow rate. Right, that is not the optimized condition. As an engineer, we have to optimize the process. So, how to find the flow velocity? Vf. How to find the settling velocity? Vs. So, Vs we can easily find with the Stokes law. Vf is equal to surface overflow rate. That's the flow rate, right? Meter cube per day per meter square. How to find meter cube per day per meter square? Q by A. Oh, Q by A. Yeah, that is our surface overflow rate. So if you equate that with the settling velocity, you can find the dimensions of the tank. See, this is the concept I am talking for the long time. If the settling velocity is greater than the flow velocity, I mean, I will zoom in. The critical velocity, yeah. Critical velocity is the one where the top particle that is entered into the system, you can see here. What is the critical speed, settling speed? Is the particle of a specific diameter gets just collected so that the vertical height in the time t. In the t is the detention time. The water is traveling from inlet to outlet. Before this time, the particle will settle to the distance of h. Then only it will be removed from the system or settled from the system. So that need to be equal to the overflow rate. That's the critical settling velocity. That need to be equal to the overflow velocity. Then all the particles are removed. If the settling velocity is greater, then even all the particles are removed here itself. If the settling velocity is lower, some particles are removed up to here and some more particles are going out along with the system. So how to find the efficiency? If the Vs is greater than Vc, all the particles are removed, so 100% efficiency. If it is equal, again 100%. If it is less than, then Vs by V will be my efficiency of removal. You got it? So that's the collection efficiency. So how much Vs by V? That's again is based on Ht by H, that is H by capital H. Okay, please remember settling velocity and overflow velocity. Settling velocity by Stokes law, overflow velocity by Q by A, that will give you the efficiency of collection. Okay. This is another major assumption. In an ideal settling tank, always it will not follow discrete. Ideal settling tank will follow the second type, that is a flocculent sedimentation. Why? All the particles will not be always discrete. It will make a collide and it will settle. So flocculent type will always follow. And settling column analysis is used to find how the settling column analysis will be there. We have a column and we have different openings. At different time, how much particle is coming out, how much we can close and we can open and we can do. This test we will do in the environmental engineering laboratory. So this is settling column analysis tank. All the water will be there, fed into the tank, I mean the column. At a different time, how the particle is settling. That we can find with this settling column analysis. Okay, so settling basin efficiency will be calculated with this formula 1 plus nvs, that is the settling velocity, q by a. So we know vs by v naught. This is vs by v naught into n. This n will be of index based on the basin performance. So if it is a very good or poor, very poor performance, n can be chosen. This is the factor. How the settling is affected? Based on the shape, size, density of the particle. This is the particle parameter. Based on the water properties. If it is more viscous water, it will not settle. If it is less viscous, easily settle. Density of the water, temperature of the water. Because settling velocity is also based on temperature, right? Why? Viscosity is based on temperature. So settling velocity is also based on temperature. That's what given in the modified formulas. Surface overflow rate, velocity of the flow, inlet and outlet arrangement, retention period, the effective depth of the settling zone. All are the factor affecting the sedimentation of the tank. How to design the clarifier, that is the sedimentation tank? First, I will compute the settling velocity with the smallest size particle, because larger particle will usually settle. This is the worst case, is the smallest particle. How to find the critical settling velocity? By Stokes law. Then I will equate the settling velocity with the surface overflow rate. How to find surface overflow rate? Q by A, right? Then I know this, I know Q, I can find the area. So area will be L into B, W. I will fix any one, L or W, or I will fix a ratio 1 is to 2, sorry, 2 is to 1 or 3 is to 1. Then I can find the L and W. How to find H? Check the adequacy of the design. So this is another important thing. H not plays any role in the sedimentation tank, because whatever the height, based on the surface overflow rate only, the particles are settling. So that we are having a new technology called tube settlers. The height is only 1 centimeter or height is 1 meter, settling is same, right? See the formula, it's not even based on the height. So height is not the factor in the sedimentation tank. So that nowadays the people are designing a tank of 1 centimeter height, that is called a tube settler. You can use this tube settler in a given area with a larger number of flow. So that's called tube settlers. Depth will be very less. Then check the design criteria, design inlet outlet arrangements. So first step will be design parameters you have to know for primary settling tank or secondary settling tank. What are the purpose? Based on that, you can take the values from here. See, recommended dimensions will be rectangular tank, means this is the depth should be between 3 to 5, length 15 to 90. Then why we have a depth in this recommended value? If it is having 3 to 5, then the tank will perform perfectly. Then circular will be having diameter and depth. You got it. Then the tank dimension, L is to be 5 is to 1 or 3 is to 1. You can choose between any value. Length, width they have given. And then circular diameter will not greater than 60 meters. Depth will not be greater than 3. Bottom slope, if you think, bottom slope is, if it is circular, it should be of 8% bottom slope. If it is rectangular, it will have a 1% slope. Why we need a slope? Then only all the settlings will happen within the slope, because more particles will be in the left side and less particle in the right side, right? Yeah. Then we have to do the inlet and outlet arrangement. Inlet you can design in a baffle format, diffusion format, submerged orifice. Water will come through this and then it will enter into this. That's a submerged orifice. Or overflow like a weir. Outlet will be of V notch. It will go out through the weir. And gratings, plates you can arrange, so that water will not be disturbed. Settled thing should not enter again. That's the major thing we have to think. As I mentioned, tube settlers. It's a new kind of sedimentation tank. Before the water travels upward, the settled particles will settle easily, and there is no need of depth, right? That is the concept. So it requires only 65 to 80% of the area of the conventional clarifier. So we are reducing 40% of area requirement. That is a good design. Energy input is very lower compared to the other sedimentation tank, because we no need of any cleaning equipment. All the particles are normally settling. We no need of reactors. All the particles can be easily removed here. But the problem is high chance of clogging. If it clogs this path, it will not be useful. This is the images of tube settlers. Water is entering into the through the tubes. You can find the tubes. So clear water is coming up. Settled particles at the bottom of the tube. You got it. So today we have discussed about the screens. Water is flowing through the screen, and then the accumulators that will grind. Then it will flow through the grid chamber, where the larger size of the particles are removed. Then it will passes through the sedimentation tank of circular rectangular shape that removes the suspended particles. Then this all is considered as a preliminary or primary treatment. Then it will go to the secondary treatment. If it is a simple water treatment, this much is enough. We can disinfect and we can supply. If it is a wastewater, we need to have secondary treatment and all. You got it? Yes. So if you have any doubt, please unmute and ask. You can post it in the chat box. I will move on to the problem solving session. So please post your answers in the chat box. I'll read the question. It will be very simple based on the things what we have discussed as of now. Okay. Okay. Please post the answer in the chat box. I'll read the question. So move on to the first question. Identify the correct statement. Okay. Regarding the primary treatment of wastewater. First statement is primary treatment of wastewater aims to remove the dissolved organic matter. Is it correct? Then second statement. Primary treatment process mainly rely on the gravity settling for removal of solids. In the primary, as I mentioned, screens, grid chamber, primary settling tank, all these three are removing only the solids, not the dissolved organic solids. So, no, not D. Option 2 is correct, right? Because we are using gravity as a principle to remove the solids. So, primary treatment process mainly rely on the gravity. So, first statement is wrong, second statement is correct. Let me take the pen. It will not remove any dissolved organic. So, this is wrong. It is relying on the gravity settling. That is correct. So, second B is the answer. Don't you think B is the answer? Why you think this statement is wrong? If you have any doubt, you can ask. Okay. Hope you got it. Okay. Nice. See here. Only large floating matters and grids are removed in the preliminary and primary tank. All the dissolved organics are removed in the biological treatment plant. That is in the secondary treatment. Okay. Second question. Appropriate velocity through the screen. We have a screen. We need to have a two velocity. One is velocity through the screen. Yes. So one is the approach velocity VA. Another one is velocity through the screen, small v. Sorry, this is capital V. This is small v. So they are asking what should be the appropriate velocity through the screen. How much it will be? 0.8 meter per second, right? Velocity will be of 0.6 to 1.2, but we can use 0.8 meter per second. You please remember this small values. That is very much important if you are designing any sewage treatment plant. Grid chamber always it will be of 60 seconds is the detention time. What is the detention time for all the tanks? You can, but screen there is no detention time. It's entering and leaving, right? Yeah. Okay. Gravel and cinders in the wastewaters are typically removed in gravels and cinders, grid chamber, bore racks, primary sedimentation, fuminating device. Yes. Grid chamber is correct. Bars cracks will remove larger particles. Primary settling tanks will remove sand particles. So this is correct. Grid chamber is correct. Gravels and cinders. You can see here. Grid chamber is second unit operation after screen. It will remove the heaviest material like sand, coffee grounds, gravel, cinders. Okay. Yeah. Fourth question. Which are the could you able to cope up with me, or shall I reduce the speed? If you want to wait, you please let me know. I will wait to guess the answer. Okay. Yeah. Which are the following units are yeah.
Sir, your speed is okay.
Yeah. Thank you so much. Let me continue. Okay. So, which of the following units are used for balancing variation in the flow rate and fluctuation pollutant load? If water is coming with a different flow, morning 10 meter cube per day, afternoon 1 meter cube per day, like that, and characteristics also are changing, pollutant loads are changing. What I can do? I can put a tank so that all the wastewaters are collected, and with the constant flow rate and the constant pollutant load, I can pump to the sewage treatment plant. This tank is called equalization tank. Okay, in industries, To maintain the pH, they will put it in a tank. Initially, if you think about paper and pulp, during the pulping process, acidic water will come. During the other process, water will be of neutral. So, my system will not handle this variation. So, I will mix both the waste and I will maintain a pH. Then I will pump. That tank is called a neutralization tank. But equalization tank will also do the neutralization process. But only the tank is maintained for pH thing, that is called a neutralization tank. Okay. Neutralization will also happen in equalization tank. So here, to maintain the flow rate, equalization tank is correct. You got it? Yeah. So answer is C. To balance the fluctuation flow, to assist in the self-neutralization, that's the objective of equalization tank. Yeah. So fifth question is, the real settling basin used for primary sedimentation. Real settling basin used for primary sedimentation usually have discrete particle settling, flocculant settling, hindered settling, compression settling. As I mentioned, ideal settling tank will have particle will settle on its own discrete settling, but it will not happen in a real system. Real settling tank will follow which type of settling? B, flocculant. I will show here. For real settling tank, discrete will not be feasible, so it follows flocculant or type 2 sedimentation, right? So answer B is correct. But our design, ideal settling tank will follow discrete settling. We have designed one particle is entering here and it will be settled here. That's a discrete settling. So our assumption is discrete, but real will be flocculant. Yeah. Match this for a circular settling tank, they are asking. Okay. Match the first column with the respective location in the circular tank. Inlet zone. For circular, inlet will be at the center of the tank. Outlet at the periphery of the tank, right? Water will come out at the periphery of the tank. So this one is C. Settling zone. Space between the center and the periphery is my settling zone. Water before moving from here to here, it will settle. The particles will settle, right? So A, C, B. D is correct. You got it? This is regarding the circular settling basin. If you see this diagram itself, you can understand. Water is entering in the center, it will move. At the periphery, it will go out. But if it is rectangular, water will enter here, water will move out here. This is the settling tank. Sorry, settling zone. You got it? As per the CPHEO, bottom slope for a rectangular tank settling basin. Why we need a bottom slope? Because more particle will, then only the water will move. Without any slope, water will not move. If it is rectangular tank, small slope is required. Only 1% is required. If it is the circular zone, then how the slope will be here? Sorry, this switch. Slope will be of periphery, 8%. So if it is a the rectangular, it should be 1%. See here, the bottom slope will be rectangular 1%, circular 8%. 1% will be towards the inlet. Okay. Please post the answer in the chat box. Eighth question is, for designing an ideal settling basin, overflow rate of a settling basin is considered equal to the settling tank. Equal to the settling velocity of which particle? I am considering settling velocity equal to the surface overflow rate. Which settling velocity I have to take? To find the settling velocity, I have to use the Stokes law. Stokes law, D, diameter of the particle I have to put. Which dia I have to put? Smallest particle, largest particle, average dia particle, or none of the above. Smallest I have to take. That's the first condition. Right? If the smallest is removed, all others will be removed. So, equate the settling velocity with the overflow rate. Find the settling velocity for the smallest size of the particle to be removed. So, that's the design of the settling tank. Okay, ninth question. For 1 mld wastewater treatment, which of the following settling unit would require least area for the same settling efficiency? I am giving same Q, but I am using rectangular tank, circular tank, inclined tube settler, square settling tank. So, which have less area requirement? Comparatively, tube settlers, right? Tube settlers will always reduce the area because it will be a flow. Upflow tube settlers having requires only not circular, inclined tube settlers. Yeah, see, plate and tube settlers are the types of sedimentation tank where 65 to 85 percentage of the required area is reduced. Sorry, 65 only 60 to 80% of the conventional clarifier area is required. Other 40% is not required. Okay, try to solve this problem. A spherical particle of given diameter is 0.02. Always convert everything into meter. 10 power minus 3 meter. That is the given data. Specific gravity is given 2.6. Okay. Dynamic viscosity, that is mu 1.002 into 10 power minus 3 Newton second per meter square. Terminal settling velocity of the particle, Vs is given. Vs is the question. So formula using Stokes law will be Vs equal to G d square by 18 mu rho s minus rho w. So or you can use G minus 1 into rho w. Anything you can use. Yeah, if you know the G, you can find 2600 is my rho s. Because and density is based on the viscosity gravity. Right? G is 9.81. D is 0.02 into 10 power minus 3 square. 18. Mu is 1.002 into 10 power minus 3. Rho s minus rho w is 2600 minus 1000. Okay, 1000 is the water, specific gravity of the water is 1 or density of the water is 1000 kg per meter cube. So if you put everything, you can find the Vs in terms of meter per second. Again convert to ms. Yeah, sorry, millimeter. Right? Use this formula, you will get this. See, G d square 18 mu rho s is 2600, 1000 is the rho w. So 0.35 mm per second is my settling velocity. Why I have used this formula? Because we have different formulas for settling velocity based on the laminar flow or transition flow conditions. Laminar flow is the one when Reynolds number is less than 1. Transition will be Reynolds number greater than 1 based on the flow properties, right? I assumed initially laminar flow and I have taken this formula. Now I have to check whether my flow is laminar or not. So what is the formula for Re? Rho Vd by mu. What is rho? Rho of water 1000. V is what are the V I have found? 0.03 00035. D is dia of the particle, I know, divided by mu. If we put all this, it's less than 1. So my assumption is correct. If it is greater than 1, I have to go with the transition flow and I have to take that formula. Okay. Hope you got this. This two formula is very important. Re formula and Vt formula based for laminar flow. This is Stokes formula. Or you can use, I will remember Gd square by 18 mu rho s minus rho w. Or G minus 1 by into rho w. You got it? Yes. So this formula will be repeatedly asking laminar flow, Stokes law to find the settling velocity. See, another question. For ensuring the head loss in a bar screen, okay, 0.05 meter. So head loss is given 0.05 meter. The maximum velocity through the bar screen having an approach velocity. So what is the formula for HL? 0.0079, right? 729 capital V square minus small v square. What is capital V? Velocity through the screen. What is small v? Sorry, small v is the velocity through the screen. Capital V is the approach velocity. So they given the approach velocity as 0.8 square minus small v square. That is the velocity through the screen. We don't know. So 0.00729 we know. What is the HL? 0.05. So if you divide this here and then add v square, you will get this answer. You got it? Right? So that's the formula you have to use. Capital V square minus small v square. approach, this is the velocity through the screen, this is the settling velocity. You got it? Formula, head loss formula. I will, as I mentioned last week, I will consolidate all the problem formulas in one sheet and I will upload in the as a reading material in Google Drive that you can find in the Swayam portal in the PMRS problem solving session. So don't worry. If you read that one page formulas alone, you will be able to solve all the problems. So I will give you a consolidated formula sheet. Okay. So don't worry. Please remember these formulas for today's problem solving session. Yeah. Another question, 15-meter long grid chamber. So there is a grid chamber of 15-meter length. Okay. Treating a 12 mld of wastewater. So Q is 12 mld. That's the flow coming in. With the flow through the velocity of, so velocity, flow through velocity is Vf, 0.25 meter per second. What is the detention time? Detention time is time the water is spending inside the grid chamber, right? Usually grid chamber should be of 30 seconds, right? How much it's there here, you will check now. Sorry, 30 seconds, so 60 seconds is the maximum, right? So here, you know the Q, you know the V. How to find? Q is converted into meter cube per day. Already million liter, so 12 into 10 power 6 liter. Again, if you want to convert liter to meter cube, 10 power minus 3. So this much meter cube per day. I have 0.25 meter per second. Okay, Q is not required here. I know the VF, I know the length. So to travel 15 meters, 0.25 meter per second, how much time? Just divide 15 by 0.25, you will get meter per second. Simply seconds you will get. Length of the grid chamber by horizontal velocity will give you. Length will be meter, horizontal velocity will be meter. Horizontal is the flow velocity, right? Meter per second. If you divide, meter will get cancelled, S will come up. That's the detention time. Most of the problems you can solve with the unit. Surface overflow rate will be equal to the flow velocity because this is meter cube per day per meter square. This is meter per second. So if you cancel meter square, meter per day or meter per second, both are same. Okay. Use this formula to find. Detention time will be second. Another question. See, 3.5 meter deep circular sedimentation tank. So circular sedimentation tank depth given 3.5 meter. Treating water that is coming out, water coming out. Q is 6000 meter cube per day. Okay. At a overflow rate, SOR is given. That is the flow rate VF to come out 40 meter per day. This is actually meter cube per day per meter square. That's that they given in meter per day. The approximate detention time is the question. Okay. Again, the appropriate detention time they are asking. You have meter cube per day. You have this one. Meter cube per day per meter square. You will get the meter square. Again, and find the area, length, and detention time. Okay, fine. See, first calculate the volume of the tank. Then you know the discharge. You can find the again. See, you have the meter cube per day per meter square, meter cube per day. You can find the volume. What is T seconds? Meter cube per day. If you have, if you divide by meter cube, you will get the D. Right? Yeah. So we have meter cube per day. Q is given. How to find the volume of the tank? We have the depth of the tank. We need to find this volume. How to find this volume? Area into depth. How to find the surface area? Surface area is meter cube per day per meter square. If you divide by meter cube per day, you'll get the meter square. That's the surface area. If you know the surface area and the depth, you know the volume in meter cube. If you know volume in meter cube and if you know the cube, you will get the time. This is the T equal to Q by A. Again, please play with the units. You will get the answer. You got it. Or else directly if you divide this 2, you will get instead of D, again you are multiplying here, you are dividing here. So instead of D, directly if you divide also, you will get the detention time. 14th question is, I hope you got the answer here. And then 14th is, in order to treat 14 mld of wastewater, 30-meter long rectangular settling tank, L equal to 30, H deep is 4 meter and then wide is 15 meter wide. Okay. Based on the information, answer the following questions. The surface overflow rate. Q is 14 mld. So they are asking surface overflow rate. Surface overflow rate is again meter square, meter per second, right? Or meter cube per day per meter square. Meter cube per day is given. Meter square is this area, not the this in this not this area. You have to find surface area. So L into W only you have to do. L into W is 30 into 50 meter square. Meter cube per day is convert 14 into meter cube per day. Divide is this. You will get meter cube per day. Already you have a meter square. The answer is given in hours, right? Hour. So convert to hour, you will get the answer. Day to hour is 24. Hour to seconds is 3600. Like that, if you multiply, you will get the answer. So 15th question. In order to treat 14 mld wastewater, they the same question, but the question they have asked is percentage removal efficiency of particle having settling velocity of 0.0003 meter per second. So Vs they have given 0.0003 meter per second. It should be always equal to surface overflow rate, right? What is surface overflow rate? I have calculated here 1.3 meter per second, meter per hour. So if you convert to second, it will be of 1.3 by 3600. 0.0000361. So see 0.0000361. 4 3s. Okay, sorry, 0 0 only 3. So Vs is less than SOR. So it will not settle. Flow is higher. So flow is faster than the settling velocity. But some particle will settle. How much particle will settle? That efficiency is SOR by Vs by SOR. So divide this 2, you will get 0.003 by 0.0036. You will get 83.3% is my removal efficiency. If it is also 0.003 surface overflow rate, I can maintain 100% efficiency. So flow is slightly higher. Understood? Before the settlement, some particles are escaping. Whatever the particle entering here are settling. Whatever the particle entered at this point, only this much height of the particle are not settling and going out. This all particles are settling. You got it? That's the settling column principle. If it enters at the lower space, it will settle faster. If it enters at the top, it will take some time. So that top particle, if it removed, that is 100% efficiency. Okay. Another 15 question we are going to see. Please answer the question. The degree of treatment required for the wastewater depends on. So how to treat? I know the characteristics of inlet wastewater. I know the characteristics of discharge standard based on the outlet quality of the wastewater based on the standards I have to treat. So this degree need to be fixed with the raw water characteristics, that is the inlet water. Decide quality and possible reuse of the treatment effluent, quality of the outlet wastewater, state regulation standards or discharge standards. I can design the degree of treatment required. So all the above is correct. You got it? Yes. So degree of treatment is based on characteristics of the raw water, decide quality of the treated water, and state government regulation. I mean, governed by the state. Yes. Second question is secondary sedimentation tank are appropriate example of. First, we have a unit operation, we have a unit process. Unit operation is dealing with only physical processes. Unit operation is chemical and biological process. Secondary settling tank is we are going to discuss next week, that is only of biological treatment process. So that is unit process. Wait, secondary. I'm sorry. ASP requires biological treatment. After ASP, secondary settling tanks always will be of unit operation, only sedimentation through gravity. So sedimentation, if it is a primary sedimentation or secondary sedimentation, it will always be gravity. So unit operation. ASP is unit process, but after ASP, secondary sedimentation tank is always unit operation. Yeah, sorry for that, unit operation, because settling is always gravity based physical force. So any sedimentation will be of unit operation. Third question, identify the correct statement concerning advanced wastewater treatment process. We have a preliminary, primary, secondary, advanced treatment process, right? Preliminary will be of screens, grid chambers. Primary will be of primary sedimentation tank. Secondary will be biological treatment. Advanced will be removal of nutrients, pathogens and all, right? Heavy metals, ions and all. So disinfection is typically considered as the advanced wastewater treatment process. Disinfection may come anywhere. Selective ion exchange is used for the removal of nitrate from the secondary treated effluent. Selective ion will not be used for treatment of nitrate. Carbon adsorption is primarily used for suspended solids removed from the secondary treated effluent. So which is called the advanced wastewater treatment process. See here. Nitrogen removal by selective ion exchange. Yeah, correct. Suspended removal by coagulation. Carbon adsorption for metals, not for suspended solids. Right? Organics only we are using carbon adsorption. You can see here. Yeah. So carbon adsorption is for organics. Suspended solids are removed by coagulation filtration. Nitrogen is removed by selective ion. Disinfection is always there in any process. So advanced process also it's there. So both A and B are correct. Carbon adsorption is wrong for solids removal. It's for organics removal. Okay. So please remember this flow chart. You can know the typical treatment process in all the stages. Yeah. Intermittent sedimentation tank is, we have two types of sedimentation tank. One is intermittent and continuous. In intermittent, water will come in, it will be stored for some time. During the rest period, particles will settle. After settlement, the water will take out. This intermittent or batch type. Continuous is water is always be there, flowing, and before it leaves, particles will settle. So here, store water for a certain period and keep it in a complete rest is correct. Allow water to flow, that is wrong. Are also known as continuous flow type, also wrong. None of the above also. So A is correct. Yeah. Which of the following is not an assumption of Stokes law? In Stokes law, we have a particle of spherical shape and it will be settling due to gravity only. It is following discrete settling. That is the ideal settling tank. Actually, it will be flocculent in real column, but in Stokes law, we are assuming it's a discrete settling. Gravity force will be acting. Spherical particle. It will follow a laminar flow. So these are all assumptions. Laminar flow RE less than 1. So think about this. Flow is laminar. RE will not be less than 10. It will be less than 1. Medium is infinite extent. Particle can settle any, can reach the infinity. That's the integration we are using. 0 to infinity we are using to find the Stokes law. So it's moving in the infinite space, not in a defined space. Particle settling is independent of influence of other particles because it's a discrete settling. It will not be influenced by any other particles. If it is influenced, then it is called hindered settling, right? So Stokes law will follow discrete settling. So A, B, D are correct. One wrong assumption is C. Reynolds number should be less than 1. Yeah. Next. So this is assumptions. Yeah. See here, surface overflow rate is capital V. Okay. SOR is capital V. That is the flow velocity, capital V. Settling velocity, Vs is U. What will be the ratio of removal efficiency of the particle having velocity less than the critical settling velocity? So efficiency will be always, which should be higher. The flow velocity should be higher than the settling velocity. So flow velocity is V by U, which is correct. The flow is higher. Efficiency is settling velocity of SOR or SOR by settling velocity. It's U by V. Yeah, Vs by Vf. Vs by Vf is the efficiency. U by V is correct. See here. Vs by Vc. Vs is settling velocity. Critical settling velocity is my surface overflow rate. Right? So, for removal, we need to use settling velocity by SOR or critical velocity. Okay. C is correct. Yeah. Type of settling most likely to occur in a real sedimentation tank. Ideal sedimentation tank, it will be of discrete. Real sedimentation, it will be flocculent. Yeah. Okay. Surface loading rate is given. Particle size is 0.02 mm. Surface loading rate, SOR, is 0.02 centimeter per second. Actually, it will be centimeter cube per centimeter square per second. Okay. Then compute the efficiency of removal of particle 0.024 millimeter particle. See, SOR itself 0.02. My sorry, I mean 0.02 size particle itself having a flow rate, surface loading rate of 0.02 again centimeter per second. Then particle higher than this will have always 100% removal efficiency, right? Because particle size is greater than the given particle size. This is having SOR means the efficiency of that particle removal will always be higher, 100% only. If it is 0.021 also, it will be settled fully. Particle less than this size will have a value 0.02 by 0.01 or something if it is given, and you have to think about that. Vs by surface overflow rate. Okay. Now, based on the particle size itself, I can find the bigger particle will always settle before that settles. So, 100% removal efficiency. All particle having a size more than the size of the particle for which the SOR is calculated, 100% removed. Okay. Match this following. Larger float particle, suspended inorganic matter, suspended organic matter, dissolved organic matter. Large floating particle will be of screen, we can remove. Suspended inorganic, grit chamber. Suspended organic, primary. Dissolved organic, trickling filter. So 4, 3, 2, 1. You got it. Larger particles, screens we can remove. Screens will remove. Inorganic only will be removed in grit. Organic will be removed in primary. Dissolved organic will be removed in trickling. Primary settling tank will not be removing any dissolved items. Okay, 4, 3, 2, 1 is correct. You got it. You can find here the answers. 10th question is, which of the following is not an objective of providing equalization tank? Equalization tank is provided to understand the fluctuation of the flow, to neutralize the flow. If balance the fluctuation is correct, balance the fluctuation in the concentration of the sewage and the correct. Assist in neutralization, removal of organics is not correct. In equalization tank, nothing will be removed. Only it will maintain the quantity and the quality, and it will be taken out. Nothing should be settled. So always it will be in a mixed condition. We need to have a mixer. Otherwise, particle will settle, right? We can't take out anything. So D is correct. Yeah. So 11th question, a bar screen is installed. Okay, a bar screen of 45 degree something angle, receiving a daily peak flow of Q 50 meter MLD. Estimate the head loss. HL is asking 0.00729 capital V square minus small v square. Okay, right. So whatever the velocity you can just put it here anyway, it will be squared. So 0.8 is given meter per second is the velocity of the flow through the screen. Flow through the screen will be always higher, and approach velocity is 0.86. So 0.86 square minus 0.8 square into 0.0729, not 00, 0.0729 into 0.86 square minus 0.67 square, you will get this answer, right? So think about the grid chamber. Dimension is given 12 meter, 1.5 meter. If you given with this type of three values, always take first as length, second as breadth or width, third as depth or height. The W or it's the D, anything you can use. LBH is the standard method of denoting the size of the tank. So liquid depth having the flow rate of 720 meter cube per hour. This is the Q they have given. Okay. What they are asking? SOR and detention time. So if I know meter cube per day, what is the unit of SOR? Meter cube per hour per meter square. So just divide it with meter square. Which meter square? L into B or L into H. Tank always surface means I have to take L into B. That's the surface overflow, right? So L into B is 12 into 1.5. If I divide this with 12 into 1.5, I will get 40,000 liter. Convert meter cube to liter, 40,000 hour per meter square. How to find the detention time now? I have all these values. So Q is there. Meter cube per hour is given. So just divide volume. Meter cube per day is there. Meter cube, if you divide, day will come up. So meter cube will be 12 into 1.5 into 0.8. All this if you multiply, you will get that, right? So if you give this, that is the volume is all the multiplication will give you meter cube. Divided by meter cube per day, will get day or hour or minute. Anything you can calculate. So answer is 40,000 and 1.2. So 13th question, calculate the settling velocity. Vs they are asking. D, radius of the particle is given. So if the radius is, please be careful. If the radius is given, multiply with the 2 to find the diameter and then convert into meter, 10 power minus 3. All the unit you have to have at same. Meter means meter, mm means mm. Please convert everything into meter. And then specific gravity Gs 2.6. And viscosity, this is kinematic viscosity. So kinematic viscosity is 10 power minus 3. So what is the Vs formula? Gd square by 18 mu rho s minus rho w. Or you can rewrite this formula as Vs equal to Gd square by 18 mu, that is the kinetic viscosity, into G minus 1. Because rho I am taking out and dividing with mu, I will get mu. That is the dynamic viscosity. Just a rewrite of the same formula. G is 9.81, D is 0.075 into 2 into 10 power minus 3 square. 18 mu is given as 10 power minus 3. Then G minus 1 is 2.6 minus 1. Directly you can substitute. Right? We will get the whole value. 0.002 meter per second is my settling velocity. Kinematic viscosity is given. Yeah. So this is the modified formula. So actual formula is V is equal to Gd square by 18 mu rho s minus rho w. That also you can calculate. Rho s, how to find? G is given. So 2600 is my rho, 1000 is my rho w. So that also you can substitute. How to find mu? Mu is given. So if you divide with the rho, you will get the mu value. Yes. Then particle concentration is high and they remain at a fixed position while settling. What type of settling is this? We have 4 types. One is discrete, flocculent, hindered or zone settling. Finally is compression settling. In discrete, one particle will not interfere with the other. In flocculent, one particle will merge with the other and then it will settle. In hindered, one particle will not one particle is fixed, other particle is fixed, but as a whole it will settle. Why? Because its settling will hinder this settling. So question is, at high concentration they remain in a fixed position, that is distance is always same, but they settle, that is a hindered settling. Type 3 is correct. Don't confuse with the high concentration. In type 4, very high concentration, all are settled there is no settling velocity, but due to the weight of the above particle, below particle will settle. That small velocity will be the settling velocity. That is type 4 settling. Because in a big tank, all the particles will settle up to here. Then in the course of time, it will reduce the height to this. So this much is distance traveled in the tank, right? So here the answer is type 3. See, position with respect to each other is fixed, and then this is changing. Then confused with the high concentration. Okay. Okay. Last question. The average flow in a municipal wastewater treatment plant is 4,000 meter cube per day. Q is given 4,000 meter cube per day. Please play with the units. You will get the answer. Meter cube per day. Convert day to hour, minute to second, anything you can do. Determine the diameter of the circular clarifier. We have a circular clarifier. We need to find the diameter. Okay, that's the question they are asking. To remove the suspended solids as average flow, assume the overflow rate S or SOR is given as 20 meter per day and depth is 3 meter, the tank depth. Okay, SOR I can rewritten as 20 meter cube per day per meter square, right? So, if you have 4,000 meter cube per day, if you have 20 meter cube per day per meter square, I can find the surface area. Easily I can find. How? Meter cube per day per meter square. If I divide with the meter cube per day, then this 2 will be cancelled. Only meter square will come up. So 20 by 4,000, I will get meter square, right? Then pi by 4 d square, that is the area of the tank, circular tank. Pi by 4 d square I can equate with that area and I can find the d value. Sorry, 4,000 by 20, I will get the meter square. Then pi by 4 d square equal to 200. Then multiply 4 here, divide it by pi, root of this value will give me d value 16 meters. Yes, not 28, 16 is correct. Got it? So, this is all about today. Yeah. Thank you so much for joining. If you have any doubt, please let me know. I'll answer. I'll be here in the meeting for next 2 to 3 minutes. If you don't have any question, you can leave the meet. So don't forget to give the assignment by tomorrow evening. Every Wednesday is the deadline for the assignment. If you have registered for the examination, please don't forget to give the assignments. Okay. Thank you so much for joining. You can leave the meet now.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you. Thank you. Yeah. If you don't have any question, I'll close the meet. Thank you all. Yeah. Let me close.